Next point is check the actuator output and compare with the P. Yeah, check actuator output after reference step that we have done in all previous projects. In our case, we get the following result. Here's our controller, PIDT1 controller, process, FP, feedback, negative feedback. If we apply a unit step here, we look for the peak here. In the first moment, no compensation comes back, so the amplitude 1 directly goes to the controller, and we can say the peak value is in both cases, in P controller case and in PD controller case, is Kc times step depth. That can be seen in the workbook, page 16. Here is clear the gain of the P controller is K, and the first response after a unit step here of the PD controller is K times step depth. So this is that's what happens after reference step, this peak value. So compare both values. P controller has a Kc of 2. Kc times step depth is 2 times 1 is 2, and the PIDT1 case is Kc times step depth is 4 times 10 is 40. Note, this is 20 times larger amplitude, larger pulse, gets 3 times faster loop. Note, this is not very effective. Yeah? A 20 times larger amplitude costs more than 20 times more than this simple controller. So yeah, this 20 times larger amplitude and then only 3 times faster loop should be very good, critically investigated in any application. Okay, let's now finalize this situation after looking on the PIDT1, because the PIDT1 has 11% control error. So with my number 8, I now finalize the discussion with our traditional full power, we can say full power controller with integrator to remove control error and differentiator to accelerate the system. Yeah. Here I have just typed down the transfer function. The transfer function, the Bode plot transfer function of the controller FC contains 4 unknowns for 3 parameters. Here the second numerator time constant in the Bode form is called TV. Note that is the same place as we have called this parameter in the PD case TD, but TD and TV in PID are different. No? TV here is the numerator second time constant, and here in PD we have called this TD. Note that should not be mixed up. In the denominator here we have the PI part, the left is the PI part, and the right is the PIDT1 part. The selection of Tn in our application goes with pole compensation, and the Tn gets the largest one, largest process time constant. Tv we select to 0.33 seconds. This is the second largest process time constant. Step depths selected by desired acceleration factor. Desired acceleration factor. And Kc comes from Nyquist final equation. Okay, so I show you how to design now the Bode plot curves. First, the PID controller has, of course, two different versions. One version is where the PI is selected with pole compensation, but of course you can combine the PIDT1 part and the PI part by using the PI version with symmetrical optimum. So there are two versions of the design, and in this version I start with the pole compensation PI. That what you have to do is first add phase of controller, and the phase equation is Fc of any omega is minus 90 degrees plus arctangent omega Tn. That's the PI part, PI phase, plus arctangent omega TV is the part of the PD part, minus arctangent, that is the phase of the PT1 part, arctangent omega TV over step depths. Okay, so for some points you have to do this job to get the phase curve. In workbook we can see this on page, I think this should be 41. Let's have a quick look into the workbook, page 41. Yeah. Okay. Okay, I have started in my workbook the version with the pole compensation. It's the second case here. So we have to go to PIDT1 controller, PI with pole compensation and TV with pole compensation, and we get the following curve. Here you see the process phase. The open loop phase is process phase minus 90 plus arctangent omega 1 plus arctangent omega 0.33 minus arctangent omega 0.033. These are the values for the curves, and we get the brown curve in this diagram. Compared with the previous Bode plot, you see here positive increase of the phase of the process. Red is a process phase, so the PID has here positive shift of the curve, and the integrator here is negative shift of the curve. And you see finally the crossover frequency, the cross point at minus 120, gives larger values as a P controller, but not so large as PIDT1 controller. So the integrator removes the speed down to the omega is here, but we read omega d is 5.8. Let's say 5.8. Now the result is omega d is 5.8 per second. Compared with the PD, not so fast, but control error, of course, xd of t goes to infinity is 0 in reference case. That comes from the integrator. So the integrator price is not the omega d of 7 point, where is the omega d value? Omega d, where are you? Here, 7.3, but now 5.8. It's just faster than a PD, but now here with the advantage 0 control error. Kc comes again out of Nyquist equation. Magnitude at this crossover frequency must be 1, is controller magnitude. Now we will get a much bigger expression than before. Kc, each 1 plus pt term gives a Pythagoras 1 plus omega dTn squared expression, 1 plus omega dTv expression. Here in the denominator omega td, it's omega tn, sorry, omega dTn. So, and finally Pythagoras 1 plus omega dTv over step depth squared expression, multiplied with process phase at a process magnitude at omega d. And from diagram, well, we have to look into the diagram. We see at this position we go up to the blue curve. The blue curve ends up at negative, what is this, 10, 11, yeah, negative 10, 11, no, 10, 20, here 16, negative 16 dB, negative 16 dB, equivalent with the vector, 0.155. So omega d is known, is 5.8, tn 1 second, tv 0.33 seconds, step depth 10. Yeah, of course, step depth is selected to 10 in my application. All these values are known, so we can solve this to Kc, and the result is then Kc. In my paper, I have calculated a Kc of very accurately 3. K3 of 3. So we can simulate now this controller in our simulation and check what happens with my result. So open this curve, open the signal block diagram, and with the right mouse button I can now adapt the values. Tn is now 1 second, Td 0.33 second, the step depth is 10. We have no limitation, so anti-wind up is not working. So it's just independent if you have mark here, have here a mark or not. Say OK, and finally we get the black curve. So I just make a recalculation, and now the black curve is a PIDT1 block, and you see final value is very good, little bit slower than PIDT1 caused by I, but much faster than PI. The acceleration factor is, let's look for the maximum here. The maximum is at time nearly 2 seconds, and here the time is 0.45 seconds, so we have an acceleration factor 4 times faster than PI, nearly 2 times faster than P. So we can just say, okay, this acceleration is possible with the same damping. but we should have a look on the actuator pulse. So that's the next step. So we make a note for the result from simulation. Uh, 4 times faster than PI. Actuator peak. Let's compare these actuator peaks. We have the step depths 1, 10. I want to fill 2 and 5, and we have here the peak is Kc times step depths. It's a measurement value for the peak value in PI case. That is step depth 1. We have a Kc of 0.76 times 1. Here we have a K of 3 times step depth 10 is 30. So you see, very ineffective. Compare this value with 30, then this is 40 times more than this, and you are 4 times faster. No? 4 times faster with 40 times more amplitude. I show you a picture in a workbook where I have calculated for step depths 2 and 5 to see this inefficiency of amplitude increase compared with the speed increase. Wait for this. Here can you see the simulation of the reference step response of our 4PT1 system, all with PIDT1 controller, all with 60 degrees phase margin, but the only parameter which is changed is the step depths. Here the green curve is that what we have seen before, and the light blue curve is that what we have seen in my simulation. Note that this is a screenshot of a previous program version. That is just an old program version, but the results are the same. The green and the light blue curve are identical to my simulation in Rec+C#. Here I have added step depths 2 and 5 value, and you see what happens with the peak value of the actuator. Here we have 0.8 and 30. That are the values I have noted on my paper. And here you see the intermediate values. Note what happens if you double the step depths from 1 to 2. Here you can see maximum nearly 2 seconds, maximum a little bit larger than 1 second. So this is not double speed, but I think 80% more speed. And the amplitude increase is factor 3. So not stop. I think this is an effective efficiency. Yeah, 3 times more amplitude, nearly double speed. That's okay. Look what happens if I now go from 2 to 5. The speed increase is, the step depth is multiplied with 2.5. The speed increase here from this 1.2 second to 0.7 second, it is okay, factor 2, yeah, double speed from this to there. But here you see the amplitude now is from 2.6 to 11, that's factor 4. So double speed with factor 4 increase of the amplitude, yeah, the efficiency goes down. And now from 5 to 10, so we double the step depth again. You see the speed increase is small, from 0.7 to 0.5, 40%. 40% speed increase and factor 3 amplitude increase. So you see, the larger the step depth, the more inefficient is the increase of the peak amplitude of the actuator. So I think go to small step depth values and you have a good efficiency without limitation of the actuator. In limitation case, note then you get nonlinear effects like wind up, and you have to work with anti-wind up mechanisms, which are only really good available in digital control systems, not in analog realizations. Okay, let's close the discussion with 5.7.9. that is a second version of PID controller, PIDT1, with PI symmetrical optimum plus PIDT1 part with pole compensation. That means, if we look on the transfer function, this part then is realized with the second version with a symmetrical optimum. This part is done in the same case. TV with pole compensation means TV is set to 0.33, the second largest time constant. What could be the reason to select this as with symmetrical optimum? The reason is to check maybe this could be better for your application than the pole compensation version. So both versions should be checked and select the best one. In our case, what have we to do? Steps. Select TV, and this is unchanged. Select step depths, this is unchanged. What now is new is, of course, for the symmetrical optimum, we don't need the phase curve of the PI controller, because this is not necessary in the symmetrical optimum design. So we have only to add the PIDT1 part. So add PIDT1 phase to process. FP. So open loop phase, or that is not really open loop, because open loop is all phases, and this is only the process with PIDT1. I can say this is a new phase curve. New is process phase plus, and now the PIDT1 part is arc tangent omega TV minus arc tangent omega TV divided by step depth. So add a PIDT1 part, then you get a new phase curve. This is done in workbook. See workbook page. Let's have a look where we are. Page P. This is this part on page 41, top picture. Top border plot. Okay, here you see phase curve, PIDT1 phase curve. That's the same phase curve as if you only have the PIDT1 design. So just with this phase curve you can do two designs. One design with pure PIDT1 controller, or with this controller and PI with symmetrical optimum. You see here with this phase curve you can just check two different design types without any additional work. Note that in the PD case we have looked for the cross point at -120. Now in the PI case, note the symmetrical optimum PI controller looks with 15 degrees negative phase value for the controller at omega d. We look for the cross point at -105 and get a new omega d value very exactly 1, 2, 3, 4, 5 at 5. Let's look what we have here. Omega d is 5. Top Bode plot. We knew this same curve then chapter 5.27 PIDT1. Yeah. Now cross point at minus 105 degree value is the new phase curve at omega d. This gives now the new omega d value. It comes from the idea that the controller phase at omega d is minus 50. That is the selection in the symmetrical optimum. Look that this value is selected in the case that we have 60 degree phase margin. In the last project I present, if the process has itself an integrator, then I will show you that there is a clear relation between the selected phase margin and the selected negative phase of the controller at omega d. So far, this cross point, new phase curve, green curve, at value minus 105 gives the new omega d value, and this was 5 per second. If we compare this with our previous pole compensation result, then we see we are a little bit slower. This is a slower design in this case. Okay, no, slower design. The Tn can be calculated with the equation for the pi phase. Fpi at omega d is selected to minus 50 and calculatable with minus 90 plus arc tangent omega d times the unknown Tn. So this is the equation to select the Tn value, to calculate the Tn value. In our case we get Tn is plus 90 on both sides gives 75 here, so we have Tn is 1 divided by omega d times tangent of 75 degrees, and the result is 0.745 seconds, a little bit smaller than our 1 second pole compensation value. This 0.7 compared with the pole compensation value is 1 second. Finally, the Kc comes exactly with the same equation here. That is the same with new values. Omega d now with 5, Tn with a new value 0.7, Tv and step depth is the same. Fp is a little bit changed, not minus 16. In our diagram, we see that the cross point, the new crossover frequency is a little bit smaller. I check 14 dB. What is the result? What amount? 14 dB. In my calculation, negative 14.2. Yeah, it is coming out of the simulation program. Yeah, but of course, if you have a handwritten Bode plot, then this is negative 14. Accurate enough for our calculation. So Kc in brackets with negative 14 dB phase process magnitude at omega d gives, and the resulting value in the workbook is 2.6. I add a simulation, and then we will see the difference. It will be small. Yeah? Pole compensation and symmetrical optimum will have small changes, but of course we should look into the simulation to get the values. So I start simulation now. The PID controller has now 2.6, value 0.745, and PD part is unchanged. So I say OK, and we calculate now the next curve. The fifth curve is this. So you see maximum is a little bit later, so slower. The final value, of course, is the same. Yeah, that's your decision if you want to go with pole compensation, black curve, or symmetrical optimum, brown curve. You see the difference is small, and I think, well, in this case, not a real big advantage or disadvantage of one of the other compared with the other curve. Last conclusions, look on workbook page 42. This table contains now all relevant designs with constant phase margin. Phase margin has no special column because the phase margin is just constant 60 degree. Here we have a P controller, I controller, PI with pole compensation, PI with symmetrical optimum, PD, PID with symmetrical optimum, PIDT1 with pole compensation, with our resulting speed indicators with the design values of the controller gain with the selected or calculated time constants of the PI controller. Here as an indication for speed in or decrease the controller phase at omega d. You see here the symmetrical optimum and pole compensation values are presented here. Here you can see that the symmetrical optimum has not so big positive phase compared with pole compensation. That is the reason why the symmetrical optimum is a little bit slower. This could be improved by just changing the TV value to a value so that this will be larger. And yeah, in both cases, here's the reference error, the control error and reference case. Yeah, of course, if you have no I, then there is an error. If we have an integrator in the controller, then the error is of course then 0. So this, I think, closes now this 4PT1 example, and I show you now in the last step what happens if our process itself has an integrator. That comes with the next chapter, next video.